Assalamualaikum and hello. My name is Hydrocarbon. It will be my great pleasure to presenting my research on determination of polycyclic aromatic hydrocarbon PAH in processed food, specifically bread, using the quick, easy, cheap, effective, rugged and safe Quechers method coupled with gas chromatography, mass spectrometry, GCMS. Bread is a staple food consumed by billions worldwide, constituting around 10% of an adult calorie intake. Bread is not only valued for its nutritional benefit, providing carbohydrates, fiber, and essential nutrients, but also for its comforting presence in daily life and its deep cultural significance. However, it is vulnerable to contamination, particularly by polycyclic aromatic hydrocarbon PAH. PAH can be found in food products as a consequence of certain industrial processing methods such as smoking, grilling, roasting, and drying, which permit direct contact between food and combustion product. Many PAH have been categorized as carcinogen, mutagen, and teratogens, putting human health and welfare at risk. Scientific evidence link PAH to increased cancer risks such as breast, childhood, and lung cancer. The problem is the presence of PAH, particularly benzoapyrene (BAP), in bread due to the contamination of bakery raw material such as water and flour, as well as during the baking process, pose a significant health risk, necessitating effective detection and analysis method. The traditional method for analyzing PAH in foods such as solid extraction and solid phase extraction are costly, solvent-intensive, and time-consuming, and require sophisticated analytical equipment. Due to this limitation, traditional methods are less practical for routine analysis. This hinders the timely detection and response to PAH contamination in food products. To address this challenge, Islamizat employed the quick, easy, cheap, effective, rugged, and safe method, commonly known as Quechers, conjunction with gas chromatography mass spectrometry (GCMS) to determine benzoapyrene in bread. However, the Quechers method is not without its limitation. Specifically, the choice of solvent and sorbent can affect the determination of PAH. Additionally, there are not many studies focused on optimizing the Quechers method using advanced techniques like response surface methodology (RSM) and central composite design (CCD). This technique could help fine-tune parameters such as solvent volume and sorbent mass to improve accuracy and efficiency. Thus, this study proposed optimizing and validating the use of the Quechers coupled with GCMS for the detection of PAH in bread sample. By employing Central Composite Design (CCD) in response surface methodology, for optimization, the study aims to enhance the accuracy and precision of PAH analysis in bread, ultimately improving food safety analysis technique. The significance of this study cannot be overstated. Our research focused on the potential to utilize the Quechers method in conjunction with gas chromatography mass spectrometry (GCMS) for the precise and efficient detection of polycyclic aromatic hydrocarbons in bread. PAH, including benzoapyrene, are known to be harmful contaminants, and their presence in food products pose a serious health risk. By employing advanced optimization techniques such as RSM and CCD, we were able to determine the optimal condition for enhancing the extraction efficiency of PAH. This technique allows us to systematically investigate and model the effect of various parameters such as solvent volume and sorbent mass on the extraction process. Our study not only provides a quantification of PAH level in bread, but also set a methodological precedent for analysis of processed food. By demonstrating the effectiveness of RSM and CCD in optimizing the Quechers method, we paved the way for future research to adopt this technique, potentially leading to more accurate and efficient food safety analysis. Furthermore, this research highlights the importance of continuous improvement and innovation in analytical methods to ensure the safety and quality of our food supply. As the demand for processed food continues to rise, so does the need for reliable and efficient methods to monitor and control contaminants. Our study to contribute to this crucial field by offering a robust and practical approach to PAH analysis in food products. Next, we proceed to the objective for this research. The first objective is to develop and optimize the Quechers extraction technique combined with GCMS for analyzing PAH, specifically benzoapyrene in bread. Second, to evaluate and compare the identified PAH levels in bread against established safety threshold and regulatory limits for food products. Polycyclic aromatic hydrocarbon PAH are a group of organic compounds composed of multiple aromatic rings. They are known for their persistence in the environment and potential health risks. PAH are primarily formed during incomplete combustion of organic material such as coal, oil, gas, wood, and tobacco. PAHs are hydrophobic and tend to bind strongly to particulate matter, which facilitates their distribution in the environment. They can be found in the air, water, soil, and sediments. Benzoapyrene BAP, one of the most extensively studied compounds within this group. It is known for its potent carcinogenic properties and is considered a significant environmental health concern. BAP is classified as a Group 1 carcinogen by the International Agency for Research on Cancer (IARC) due to sufficient evidence of its carcinogenicity in humans. It is known to cause mutation in DNA and is associated with lung, skin, and gastrointestinal cancer. Polycyclic aromatic hydrocarbon PAH are environmental contaminants that can enter the food chain during food processing, preparation, and cooking. They are primarily formed during incomplete combustion of organic materials and can be found in various food products, including bread. PAH, notorious for their carcinogenic properties, can find their way into bread through several pathways. Firstly, during baking, especially in traditional wood or coal-fired ovens, high temperatures can lead to the formation of PAH. Secondly, PAH present in the environment, whether from industrial emissions or outdoor air pollution, can settle on grains or other raw ingredients used in bread production. Lastly, airborne PAH can also land directly on bread during storage and transport. The European Commission regulates BAP levels in certain foods, including bread, not to exceed 1 part per billion. One of the most significant advancements in PAH analysis is the Quechers method, which stands for quick, easy, cheap, effective, rugged, and safe. Developed originally for pesticide residue analysis, Quechers has been adapted for PAH analysis due to its simplicity and efficiency. It involves two main steps. First, the extraction of analyte using acetonitrile or other solvents, followed by a cleanup step using dispersive solid phase extraction. This method effectively removes unwanted metric components, ensuring high recovery rates and accurate analysis of contaminants like pesticides, veterinary drugs, and even polycyclic aromatic hydrocarbons in complex matrices such as food products. Its versatility and robustness have made Quechers widely adopted in laboratories worldwide, offering cost-effective and reliable results while meeting stringent regulatory requirements. The methodology involves several stages. The first stage is a Quechers extraction. The Quechers method starts by placing 5 grams of homogeneous bread into a 50 ml centrifuge tube. The sample was then spiked with 100 mg per liter standard solutions and 40 ml of acetonitrile were added. The mixture was vortexed for 3 minutes to ensure thorough mixing. After vortexing, 2 grams of anhydrous magnesium sulfate and 1.5 grams of sodium chloride were added, and the mixture was vortexed again for 3 minutes. The mixture was then centrifuged for 5 minutes and 7 ml of the supernatant were transferred into 10 ml amber vial to a dry under a nitrogen evaporator and allowed to dry completely. Once dried, the residue was reconstituted in 0.5 ml of acetonitrile, mixed and sonicated for 3 minutes to ensure complete dissolution. The solution was then transferred to a tube containing 60 mg of magnesium sulfate and 20 mg of silica, vortexed for 1 minute and centrifuged for another 5 minutes. Finally, 0.5 ml of the clean extract were transferred to an amber tube, and 1 microliter was injected into the GCMS for the analysis. The GCMS analysis was conducted with the ejector temperature set to 260 degrees Celsius and operate in speedless mode. The carrier gas flow rate was maintained at 3 ml per min and the injection volume was 0.5 microliter. The column temperature was programmed to increase from 150 degrees Celsius to 200 degrees Celsius at the rate of 10 degrees Celsius per minute held for 2 minutes and then increased to 260 degrees Celsius at the rate of 15 degrees Celsius per minute held for 5 minutes. For the validation of the studies, the method's linearity was assessed by plotting a calibration graph with concentration ranging from 100 mg per liter to 400 mg per liter. The limits of detection LOD and quantification LOQ were calculated using the standard deviation of the response and the slope of the calibration curve. Precision and accuracy were evaluated through the calculation of the mean, standard deviation and relative standard deviation and a recovery study. A calibration graph for benzoyl BAP was constructed using 4 different concentrations ranging from 100 to 400 mg per liter. The retention time of standard BAP from GCMS analysis is 1.933 minutes as you can see behind me. By using Center Composite Design CCD of Response Surface Methodology RSM, we optimize the Quechers method. The optimized parameters are 50 ml of solvent volume and 20 mg of sorbent mass. Under this condition, we achieve significant analytical performance with a linearity range of 100 to 400 mg per liter and a coefficient of determination of 0.9892. The LOD and LOQ were 59.55 mg per liter and 180.46 mg per liter respectively. For recovery study, we constructed 2 different concentrations, which is 150 mg per liter and 350 mg per liter to get the average relative recovery and RSD percentage. The average relative recovery and RSD percentage that we obtained are 112 with 1.31% and 110 with 1.09% respectively. In conclusion, the optimized condition for the study were achieved by setting up the mass of solvent and volume of solvent using CCD. The optimized conditions are 20 mg of solvent and 50 ml of solvent. The method was successfully applied for the extraction of BAP with an average relative recovery greater than 90% and a significant lack of fit model used. For future research, we recommend experimenting with different types of sorbent besides silica, such as graphitized carbon black GCB or C-actin, to offer different selectivities and efficiency in capturing BAP. Additionally, exploring the box beacon design, a type of RSM, could efficiently examine the response surface using a reduced number of experimental runs, leading to a rapid determination of optimal conditions. And that's all from me. Thank you for watching.